domain response at length, and I'll have your quizzes this Friday. What I want to mention now is two things about the last parts of this chapter, and then tell you that of chapter 9, then we'll be into chapter 10, which is microwave. All right, so we have, I'm not sure how many lectures left, but we don't have a full 4 weeks. I know that. We've got till Thanksgiving a week and a half, and then after Thanksgiving, I think we get a week, don't we? About a week. So we're wrapping it up. This is going to be the last bunch of material. And today what I want to do is talk about common mode chokes first, and then shields. But you all have had filters, right? High pass, low pass, band stop. What class did you have in? Circuits?
I did an RF lab.
Did y'all have to take RF lab?
Yes.
All right, if you've had those already, they're in the book, but I figure, in electrical and computer engineering, you get filters in a lot of classes. And this is not really EMAG, this is more lumped element stuff, circuit design, the way he presents it. The filter I'm going to show you is going to be one you're already exposed to. You have basically a thick shield, and you have an electromagnetic wave incident on it. It's how much penetrates in the shielding effectiveness. I think we talked about that already once when we talked about skin depth. You all remember that? With skin depth? I'll go through it at length. So today, this is the very last topic in chapter 9, and it's using common mode chokes. And I want to show you how they work. And they're not hard to understand because everybody here has had transformers, right? You all have transformers and mutually coupled circuits?
Yes.
All right. Who has it? Did anybody not? You didn't? You didn't have anything with transformers or mutually coupled circuits?
I hadn't had power yet.
Are they not in circuits? Is it only power where you get them?
Yeah, I think they were.
They are in circuits, they're in circuits.
Hey.
Are they? You didn't go that lecture, huh? All right, no, they are. They should be. I know, because I teach that course every once in a blue moon. Then I teach the non-EE version of it, negative transfers. It's considered an essential element, a lumped element. Inductors, capacitors, op-amps, resistors, transformers, and generally speaking, they also talk about mutually coupled circuits or rectifiers too. You got diodes, right?
Yes.
All right, then that's basically it in a nutshell. So today we're going to be talking about common mode choke. And it is a transformer. I'm just going to tell you the way it's laid out. When we build these, you're going to take, it's a simple ferrite donut like this. Think of a donut made of something metallic that's very small. And what you're going to do is see two wires like this. They're going to come around and wrap like that. And we're going to have two currents. This is going to be I1, and this is going to be I2. All right? And those currents can either be both in the same direction, or they can be in opposite directions. Now, this ferrite donut is effectively a transformer. But the reason I'm showing you this is because in the real world, if you have EMC problems, this is one of the cheapest, most common ways to deal with it. We have these little ferrite donuts. They got a diameter no bigger than a penny to a nickel. And they're basically like if you took a thick straw and wrapped it into something that had the perimeter of a nickel or a dime or a penny. That's the dimensions we're talking about. And then the wire would be shellacked or it's coated copper wire. You don't need to use insulation, anything more than a thin piece of copper or something. I mean, copper with shellac. Y'all know what I'm talking about when I say that? They're just regular copper wire. They dip it in shellac. Doesn't have much standoff voltage, and they'll wrap it around here. And they'll get somewhere between 10, 100, no more than 150 turns usually. But it'll do everything you want. Here's why. So on this, you know how there'll always be a dotted terminal, right? So that is an effective transformer, and we make these and we design them, and we can even estimate the inductance of this. I think Dr. Gross goes through and he talks about, he takes a straight piece of transformer material and he just wraps a bunch of turns and So I'll do it that way to show you. and this is probably the easiest way without getting into the physics to understand. If you have something metallic, and this is going to be iron core, and then I take a bunch of transformer windings like this, just coils, you're wrapping them tightly, and I put a dot here and I call this I1. Without doing anything more, if you were just given this for a point of discussion, you get a job interview. Now, I don't know if this happens. I've never heard of this one, but I can imagine it in my head because I know that employers are more and more suspect of how valid degrees are from schools. They see people, he's got a 3.0 from, I don't know, Georgia State or something, in electrical engineering. Okay, how's such a word? And I'm not sure that he knows what he's doing. So I'm going to start going through some basic questions and make sure. First thing is, if current's going in there, which is the direction of the magnetic flux based on your understanding of either physics or engineering? How can you know? You're right, but how do you know? Because you all have right hands, I hope. Kinda, yeah. Well, if you take your right hand and take your index finger, put it in the direction of current, and wrap it around that thing, your thumb on your right hand points in the direction of the flux. That's magnetic flux. That's it. I don't care how much. I'm not going to get into reluctance. We could calculate all that if we had time. But you remember doing magnetic circuits back in EMAG 1? Remember there was an effective resistance, magnetic resistance called reluctance. There was a magnetic voltage called MMF. Remember that? It was N times I. You all remember that? So if we wanted to calculate that, you're not going to be responsible for this, but just for the future. What you could say is I have this fictitious magnetic voltage, Ni, and I have a fictitious reluctance here, and that's equal to the length of this thing over the permeability of that thing divided by the cross-sectional area. Y'all remember that? How many do? I mean, just for the point of discussion, people ask this. If you go to work for the power company, especially if you're doing anything that deals with large amounts of electric power or wires off the line, you're going to be dealing with something like this, and somebody will come down and ask something like this. Well, if that's the reluctance, for now we're going to leave it as, well, how much flux, magnetic flux is going there? And the magnetic flux is like current, electric current, and it's simply going to be MMF or Ni divided by that reluctance. That's how you calculate it. Y'all remember that? It's that simple. That gives you an estimate. Now, that's the first winding. Now I put another set of windings on here. And for my other set of windings, let's see if I actually have some ink in there. Now let's start. I come down here. Doesn't matter how many turns either in this case. So here I'm going to put a dot. Now, you don't have to do it this way. I think Gross tells you to dot one of the terminals, but I don't remember how he does it.
Yeah, he does.
And he'll say, go ahead, put current into it. You could be the bottom one, doesn't matter. So I'm going to put current into it, and I'll call this I2. I just guessed. Now, if the flux created by that second turn of wires is in the direction of the flux created by the first turn, then it's in the right place. But if it's not, if it's going the opposite way, you simply erase that dot and put it down to the opposite terminal. Y'all remember that? It's that simple. So anyway, that's basically what you got here, over there, and I'm just straightening out that core and showing you what you got. But the relationship for these things, this is V1 and this is V2. The standard form for the induced voltage on a magnetic circuit, this is not going to be an ideal transformer here, it's going to be a magnetic circuit. If we let the coupling factor go to 1, it becomes a transformer, an ideal transformer. But I don't do that kind of stuff in this class. Dr. Gross may, or in the 400 level courses, you'll see this. So, what does that really look like is this in terms of the math. We're going to assume it's at a constant frequency. V1 would be J omega L1. That would be the self-inductance of the primary times I1 plus, I'm hoping one of these has a little bit of link, plus J omega M1, I'm just calling it M, it's the mutual I2, And then V2 is equal to J omega M I1 plus J omega, and this would be L2 I2. Do y'all remember that for magnetically coupled circuits? If you don't have any coupling, if the mutual's gone, they're just what? The impedance of the self-windings. It would just be J omega L, right, for either side. But the M has to do with the coupling between the two. A lot of times it's defined, I didn't even show you the way transformer, magnetically coupled circuits are usually drawn, but it's like this. And this would be V1, this would be V2, this would be I1, and this would be I2, and that's the actual expression for it. Y'all remember that? Okay, now we get into this circuit right here, which is the same thing as I've shown there. And when you do any of these common mode chokes, you assume L1 equals L2. And the mutual is going to approach the value of the actual self-inductance. Now there's a very important reason for that. You're about to see it. Everybody got me on this, class? So now we come to this. And we talk about two cases. When we talk about common mode chokes, here's the reason they're there. I want you to see this. If you have a standard transmission line, think of a standard like extension cord or coax cable. Please listen to this. Believe it or not, some people this doesn't ring true to, and you can get yourself in trouble. And you'll embarrass yourself in an interview. You all know that you will have a current in this direction, and the same current will return here. In 99.99% of the applications that you deal with where you're communicating either power or just communication information from one source to the other, current flows, and the same amount of current flows one way as returns. Do you all follow me on this? This is real important. Some people don't know that. Forget about the voltage. The current is the thing that's so important. So in a coaxial cable, regardless of the frequency, the outer rim, that foil, will carry some current I. The exact same amount of current. If you cut that thing and look at the time signature of the current, the same magnitude, opposite direction current will flow in the core. There's no time phase difference. Y'all follow me on that? Important. So, that said, if currents are like this, where you have I1 going this way and I1, or the second current right here going that way, and I1 is ID and this one is ID in magnitude, that's called a differential current because same magnitude, opposite directions, they're considered differential. Do y'all follow me? It's just terminology. Common mode is when both currents go in the same direction, and you don't ever want that. Y'all hear me on that? You never want currents in the same direction at the same time for any kind of a transmission. The reason is, the only way they can get back to the source that created it is destroying some kind of equipment. For instance, when lightning hits, and I've seen the aftermath of this, personally up close. I watched a house burn down one time with my student. I don't think I told you guys this, but I had a student named Paul Rye, probably in 2008 to 10. Real bright kid, and he had, it's his second degree, his first degree is in business. His father worked for the power company. I don't think I can get in trouble for this, but I might. Anyway, and he had built in his dream home on top of a hill that had a lot of granite and rock under it, which is not very good conductor. Got it? All right, and there was lightning hitting all around, killing trees. So naturally, he was going to do some lightning protection. He had the stuff on his property, he didn't put it up. My students tell me about this problem and that he needs to put it up like now. Lightning doesn't consider this is your dream home. Lightning destroys anything it can. And now here's the thing, he's telling me trees are being hit all around. And he actually had a strike near his house that had the concrete in his driveway blow up. You know what the rebar is that they put at the base of all these things? That means current was flowing in there hot enough to cause the water to expand and blow that thing up. I'm thinking, well, he works for the power company, he must know what he's doing. So I get a call and this is God's honest truth. at like 2:30. He's in my class. We had just talked about this very thing, like I'm talking to you, and how filtering, common mode filtering. This was more to do with shielding at that time and preventing and proper grounding. And he's hysterical. His father's house was struck. A pole around there got struck. It's on fire. The fire department's there. And it was, I went there, I couldn't believe it. What had happened was he didn't put up the lightning. The only thing it was is this. It's a long piece of conducting wire hung way over the house. It causes a canopy of safety under there. Do you all know what that is? It's like a tent of safety when you hang that wire. That wire, if it was properly grounded, would have saved that guy's house. And then so I was there in the meantime. The fire department's getting there and they're doing this. What he didn't tell the fire department, the emergency management, he had a whole bunch of guns and ammo. I mean, a lot of ammo. and you know, inside a gun safe is one thing, but when you have hundreds, maybe thousands of rounds, and there's a fire, things happen. So we're there, and all of a sudden, bang, bang, bang. It sounded like a real, honest to gosh, if you've ever been around automatic weapons going off, I have at Eglin Air Force Base. It sounded like somebody just opened up. And man, you want to see people running for cover and everything. And I was one of them. I never knew anything like that could happen to a guy that knows that much. But he just, put it off. So don't put off safety. and this is related to that. It's not lightning hardening, but it's related to that because those lightning currents come down. And what they'll do is they go down the coax cable. There's a portion of that current that bleeds off to the center. And then they jump. They don't, the lightning current this way is not the lightning current that way. They jump and they go to the easiest way to ground, which is right through anything they can get through, which happens to be things that they heat up in a tremendous way and start fires. So that's the moral of the story. Back to this. Okay. So differential currents you don't want to stop. Common mode currents you want to stop. Okay? We want to stop those. So how do we stop them when we do this? We'll first talk about these voltages related to differential mode currents. Has anybody been around anything that's been struck by lightning? I mean, direct hits. You have trees or what?
Yeah, tree.
My PhD thesis was on late-time electric field signatures related to lightning. I had to learn a whole bunch about lightning damage and stuff like this. It's terrifying. When lightning hits, there are a thing called dendrites. They're like root systems of glass in soil that's very dry with a lot of quartz. It's amazingly damaging. I didn't realize it was quite that damaging until I looked at some of this stuff. Anybody else? Anybody have a TV knocked out by lightning? My wife did. Years ago in an apartment complex. She had the coax cable. This was a long time ago with a vacuum tube TV. And lightning hit that thing and it destroyed her TV. She was scratching her head thinking, how in the world can that happen? But it did. It came through a coax cable. And it was, remember, common mode currents. So that's a little more to know. All right, so with differential mode currents, here we know I1 will be equal to minus I1 will be equal to IB, the differential current, and I2 will be equal to minus IB. Means they're in opposite directions. So I drew this kind of sloppily, but I'll get to this. Right here. So when we have a transformer like we do there, and I'm calling this I1, and I'll call this I2, and this is plus to minus V1, plus to minus V2. I'm just trying to show you this represents this. And I look at this, I1 equals minus I2 is I differential. When we look at V1, that's equal to J omega L, J omega L1, times IB, and then it's going to be minus J omega M I2. Now here's why. Because that I2 is going to be same magnitude, opposite direction, so the negative side right here denotes that. Y'all follow me on that, guys? How many understand that? I'm not going to spend a lot of time on this if I don't have to. All right, So this would be the equation, and this is ID for differential mode currents. Y'all with me? Now, if you take a look at the impedance of this, if we just take V1 over ID, this would be the impedance of the first coil. Y'all follow me? Voltage over the current causing that voltage is impedance. Y'all follow me on that? So this becomes J omega, and it's L1 minus M ID, or sorry, times that. This is the effective impedance of this coil right here. I'm going to draw the circuit so you can see it. Now, if you look at the same thing and do it for V2, right here, V2 itself would be J omega M, it's I1, which is ID, it'd be minus J omega L2 times ID, because I1 is equal to minus I2 is equal to ID. Y'all with me on this? So here's the differential currents and the voltages they cause. That means V2 over ID, which is the impedance of the second coil, is really going to be equal to simply J omega M minus L2. Y'all agree with that? Now I can spend more time on this, but here's the real thing you take of it. You can reverse that if you want in terms of the signs. But here, if you look at just Z1, it'll have the same magnitude as Z2. And you look at this in the differential mode. I'm just going to put an impedance here, Z1. It's going to go down, hit some load, come back. Here, Z1 and Z2 have the same exact magnitude. Promise you on that. In terms of the magnitude of the impedance. If you looked at the net impedance here, Zn, it would be equal to 2 times J omega, just magnitude of Z right here, J omega L minus M. And here we're going to assume L1 is equal to L2 because that's the way you build common mode filters. You always have the same number of turns in the primary and secondary, therefore the primary inductance has to be equal to the secondary self-inductance, and the mutual is the same for both. Y'all follow me? Now, if you look at this, y'all agree with that, first of all? What's the one thing you notice about if the self-impedance, if L is equal to M, what happens?
0.
It's 0, right? And the whole idea is when you have a common mode choke, you don't want this thing to interfere with any normal communication or a power or information, and it won't. If M becomes very close to L, and most of the time, because this is going to be a ferrite right here, and all the flux is going to be linked in there, M and L are almost identical. Y'all with me? So the idea for a common mode choke is you want no impedance, no limit to the actual standard differential mode. Now, when it becomes something where you have a common mode signal, when I1 equals I2, I'll put it over here, and this is important. So when I1 equals I2 equals I, and you can call it C. This is a common mode currents. And then you get V1, so here we're going to have currents in the same direction, both of these same magnitude and phase. Then you get V1 is equal to Jm, or J omega, and it's going to be L. I'm just going to say L1 is equal to L2 for this one, times I1 plus J omega M, or I'm sorry, I common, and then V2 is equal to J omega M I common plus J omega L I common. And here you can see that V1 over V1 over I common is equal to V2 over I common is equal to the impedance of coil 1 and 2, and they're equal to J omega M plus L. Y'all follow me on that? How many see this? So when you have common mode, what happens, there's not a subtraction of the mutual from the actual self. It's an addition. And generally speaking, because L is about M, this is about equal to J omega times 2 times L plus M. Or times 2L for one coil, and that means for both coils, and I'll draw it right here so you see it. So if you were looking at the impedance equivalent in series for this, each one of these right here would have Z common equal to J omega times 2 times L approximately. So whatever the self is, it is the mutual. You could put M plus L if you want, but usually the self and the mutual are about the same. I'm going to give you a few problems with this where they're not quite the same, so you have to do some calculations. Y'all with me on that? Now, in common mode for non-lightning events, lightning is a different story, but if you think about common mode currents, a good question is where do they come from? And you all know, if you know what a ground loop is or not. Do you know anytime you have a large piece of wire, either running through the wall or anything like that, and you have a time-varying magnetic field through there, then you get induced voltage. Are you all with me on that? So if you have an extension cord, or you just have a wall outlet there, and it's got 2 wires in parallel running around the room, right? And I'll erase it and show you what I mean right here. Then, interesting things happen. So, I'll start with one coil wire. Suppose this represents just one line of something that goes, we'll assume that that wire goes all the way around the room, all right? With me on this, guys? I'm just trying to give you something, it's a visual aid. And there's a magnetic field that's perpendicular to this, that's a function of time. And it's going into the board. Same magnitude everywhere, right? And if this loop has area A, then the total magnetic flux through that loop is simply equal to the B field right there, magnitude times A, assuming it's perpendicular to that loop. Y'all with me? What's the EMF voltage developed here? Anybody? Minus the time derivative of the magnetic flux with respect to time. Y'all remember that? So if you take a time derivative of that, you're going to get the area, and if it's periodic, times minus J, times J omega, times the time rate of change of the B field with respect to T, or sorry, then it's just the B field. In EMC, we do the calculation entirely. We estimate these things, and they're pretty darn close for a given situation. Now that's for one turn, all right? For one cable. That'll be the induced voltage. And if there's nothing to limit the current in there, but there usually is, then you could calculate the current by taking that induced voltage, dividing it by the impedance of that frequency. Y'all follow me? Now what if you have a simple extension cord where 2 of these go in parallel? Y'all see that voltage is across both of those, driving current in the same direction in both of those? So that's a common mode current, and it's caused by a ground loop that's actually having magnetic field inducing it. You with me? There's other methods for common mode current to get into a system. And you probably see this fully. But when you start building stuff and putting that stuff into an actual system that has to plug into that wall, common mode currents that come from that wall outlet, first of all, anything coming out of that wall outlet has to go back into it, hopefully, right? Well, that's not always the case, and that's where common mode comes in. Because then they'll arc through and go through something called a green wire, you know, the actual earth ground. Are you familiar with this? And that's when all heck breaks loose, and it does happen. And people say, well, it can't go a direct route because there's insulators. But you all know if you have a time varying voltage, you have capacitive current, don't you? So there's still a way, and common mode currents are notorious for causing noise and problems in systems that need precision, high degrees of precision. So just remember what I'm saying. A lot of this will make sense in the right context, and you'll have problems of your own with this thing. Are you with me on this, guys? So that's common mode chokes in a nutshell. Next thing we're going to do is just a bit on shielding, and I want to tell you one thing about shielding. There are probably books written on how to shield systems. It's a very broad and deep topic. The simplest shields are just thick pieces of metal, and it's the ones 99% of everything uses. All right? So I'm going to do that. I'm going to do shielding next. And then we're into the next chapter. And you have all the tools for this. I even think I gave you a problem that's directly related to this earlier. What time is our football game this weekend? 11?
11 a.m.
Oh, yeah. So much for sleeping in. All right. Okay. So now shields. Now, here's a shield in a nutshell, and we'll do it. It's a thick piece of conductor usually. Just show something like this with a thickness, call the thickness T. How's that? Thickness T. And this shield is going to have a conductivity sigma. It's going to have a permittivity epsilon, and it's going to have a permeability mu. Now, in the past, you usually assume mu is just mu 0 and mu relative is 1. It's not true for shield. For steel, for instance, 1045 steel that's used everywhere, mu relative at the frequencies of interest for shielding is about 1,000. Now the conductivity is a little less than iron, or in copper, but that mu relative becomes important. Epsilon is about epsilon relative equal 1 for almost all shields made of conductors, almost all. So you don't have to worry about epsilon relative, but you have to remember to keep an eye on mu, all right? So once you have a shield like this, what is it used for? Well, it wants to stop this. It wants to stop an incident electric field from penetrating it. And the way they always talk about this when they deal with shields is they want to find out how much transmitted field will arrive that's a proportion of the incident field. So we're going to go through this. Do y'all remember doing that earlier? You do? Okay. We're just going through it again. We're going to talk about shielding effectiveness. This isn't hard, but believe me, when I do this, what I notice is there's small things that people miss that make big differences in the answers. So please watch it. So the first thing we always do is we're going to get I'm going to assume this, and you don't have to, it doesn't have to be true, but unless there's a very good reason, I assume it's air on both sides of that. In other words, the shield is in our environment. It's not on Saturn, and it's not in a high-pressured environment. The next thing we do, we assume it's at a constant frequency, so we do things in the frequency, not time domain. So we talk about the intrinsic impedance eta of the shield, and that's equal to the square root of j omega mu over sigma plus j omega epsilon. Now, in realistic shields, they're real good conductors. So for realistic shields, sigma is always much, much greater than omega epsilon. Y'all follow me? Good conductors. If it's a good conductor, eta shield becomes this. square root of j times the square root of omega mu. Oh, well, actually, I'll do it this way. I take a step back. I wanna just mention this to you so you can see it. Know with me that is eta, right? That's the intrinsic impedance of the shield. It's the ratio of E to H. Now, if this is the case, then that's true. Do y'all see that? Let me go to the next step. So this is equal to the square root of j over, or j omega mu over sigma. Y'all agree with that? Now the square root of j is something I talked about before. Remember that the square root of j is really equal to the square root of e to the j pi over 2. Y'all remember that, class? And that's really equal to 1 plus j over the square root of 2, isn't it? If I wanted to do it that way? I don't have to, but I can. So I can write this as either 1 plus j square root of 2 times the square root of omega mu sigma, or I can write this as 1 plus j times the square root of pi f mu over sigma. The reason I'm doing this is omega is 2 pi f, and if I bring the square root down here, the 2's cancel. It's just showing you other ways to write this. Probably the most common way to write this is this. It's just e at j pi over 4 or 45 degrees times the square root of omega mu over sigma. All of them are correct. That's probably the most common one because the angle is pulled out right there. Now, that said, now we start going through what you need to calculate. On a problem like this where a signal is coming, some is scattered back, so we have some E reflected here, correct? Some is transmitted, and I'll call that E transmitted 1. Y'all follow me on this? Now the transmitted signal right here is actually going to exponentially attenuate, and this will fall at a rate of e to the minus alpha z, where z would be the thickness. I'm going to get to this exact in a second. I'm just putting this up here to jog your memory. Y'all remember that? Once it's in the shield, the magnitude goes down. It exponentially decays. So before we do any of that, we get the reflection coefficient right here. Let me do a few other things too. So I'm going to make this, since I got the thickness, I'll make this the z-axis right here. And I can make this 0 and this d, but it won't matter. So now call this boundary 1 right here, and call this boundary 2. And I can say the reflection coefficient at 1 is simply eta 2, or eta shield, minus eta naught over eta shield plus eta naught. And I could take a look at the transmission coefficient at 1, which would be equal to eta shield over eta shield plus eta naught. Y'all remember that, class? Anytime you're talking about reflection coefficients, the impedance you're going into minus the impedance you come from over the sum of the two. The transmission coefficient is twice the actual impedance you're going into over the sum of the two. Do y'all remember this stuff? Okay. So we have that there. There's something else we have. We've got to get the transmission coefficient here, or I mean transmission coefficient, and really we don't need the reflection coefficient there. But the transmission coefficient in 2 would be equal to, now look, I'm right here. So the wave's coming, some of it gets in here. This is inside the shield. Now when I go from shield, in region 2, it goes from shield to free space, right? So eta I'm going into would be eta naught. So here, it would be 2 times eta, the transmission coefficient would be 2 times what I'm going into, which would be eta naught over eta naught plus eta shield. Do y'all agree with what I've shown you so far? I'm going to show you the approximations too. If you look at this, what happens? if we take a look at what's really gonna happen as, since we know that eta shield right here is much, much less than eta naught in magnitude, right? We're gonna show you how these things simplify. And please watch. So what does eta 2 approximately become? If eta shield is much less than eta naught, what do you see happen? Eta naught dominates, right? This thing's gone. What does it become? 2, about 2, and this is important. Now, when I look here, what does that transmission coefficient become approximately? Tell me about this. If eta shield is much, much less than eta naught, what do you see happen? This becomes just 2 eta shield, right? Over eta naught. Y'all see that? Take a look. Eta shield's much less than eta naught. Say this is 1 ohm, this is 377 ohms. It's about 377 downstairs, right? Divide that in to eta shield. Y'all follow me? All right. And then finally, this one, what happens? Just look at it for a second. Now, this isn't quite true up top, but what is the reflection coefficient about? If you look at this, since eta shield really is not a factor, put a 0 in. Minus eta naught over plus eta naught, it's about -1. So the magnitude of the reflected wave is about the same as the incident. Not quite, but y'all follow me? Now we go through the whole thing and show what goes on. So, when I look over here, and I want to figure out what the electric field will be over here, I have an incident field. If you listen to me, I think it'll help. Incident field hits. Only thing I care about is how much is transmitted in. So I multiply the incident field by the transmission coefficient. This is going to be E transmit. So I take, and that's the transmission coefficient in region 1, which is right there, right here. Then it's inside. Now, inside what happens? It exponentially decays, right? Y'all with me? We know, and if I put alpha down there, but you know that gamma in the shield is equal to the square root of j omega mu times sigma plus j omega epsilon. Do y'all remember that? If you assume that sigma of the shield is much greater than omega epsilon, which it is, gamma of the shield will be approximately equal to square root of j omega mu times sigma. Y'all see how I ignored the omega epsilon? With me? Now, what happens then? Well then, I'll put it right here. Gamma of the shield is equal to the square root of j omega mu eps, or mu sigma, square root of j is 1 plus j over the square root of 2 times the square root of omega mu sigma, right? And that means it's what, really? It's the square root, omega's 2 pi f, so it's pi f mu sigma times 1 plus j. The reason I did this is, anybody remember what the square root of, or what is 1 over the square root of a pi f mu sigma? Anyone? Skin depth, remember? Sure. Skin depth was equal to 1 over the square root of pi f mu sigma. So I can rewrite this, and it's written this way a lot of times. It's just 1 over the skin depth times 1 plus j. And that means alpha in magnitude is beta is equal to 1 over the skin depth. That's the only thing you take from that. So now that I have this, the magnitude, and here I'm going to do something. I'm going to put magnitude of the transmitted field is equal to magnitude of tau 1. And then it's going to be, I guess, times the incident field you can put here. It's going to be e to the minus alpha of the shield times the thickness of the shield. So now I'm right here, right? With me on that? I mean, Basically, I find out how much gets in, and then I let it exponentially decay as before, right? Now, what do I do right here before it gets out? Anyone? What do I multiply anything on this side to get to this side by? By transmission coefficient, right? Transmission coefficient from shield to air is transmission coefficient of 2, or it is, can you all read? 2, right? So it's just this times 2. So if we look at the ratio of transmitted field to incident field, we see that it's just going to be approximately 2 times magnitude transmission coefficient 1 times e to the minus alpha d. And here, alpha is just equal to square root of pi f mu sigma. And that's always the truth. That's about what it is. But now we talk about something called shielding effectiveness that you've heard before. I'll put it right here. Y'all remember what shielding effectiveness was? Anybody? It's always in dB for starters, right? I mean, shielding is always measured in terms of dB because there's orders and orders of magnitude. So dynamic ranges are incredibly large. So when you talk about shielding effectiveness, and it has a positive number even though it means attenuation. It's 20 times the log here of the magnitude of the incident field over the transmitted field's magnitude. Y'all follow me on that? It's just the ratio, but it's an inverse ratio. You with me? Now if they put a negative sign in front of it, then they reverse those. So the shielding effectiveness for us is approximately equal to 20 times log base 10 of 1 over, and if you look at this, it's 2 magnitude of the transmission coefficient at region 1 times e to the minus alpha d, and that's it in a nutshell, and that ends that chapter. So that's shielding effectiveness. How many remember that, basically, or remember the actual process for getting the electric field transmitted versus incident? Y'all remember doing that? That was chapter 6, wasn't it? Way back in the day. So this is, it applied specifically to a shield, and that shielding effectiveness is what you care about. All right, I'll give you some homework, I'll bring you your stuff next time. So the logical question is, well, is there a quiz on Friday, right? It's not a logical question.
It's a lot of questions.
All right, there it is. It's a loaded question. What did
No,
you
I
say?
said it's a logical question.
Yes. Sorry. Anyway, yeah, and it will be on the stuff we covered today. So it's either going to be, and I'll give you homework with answers, either going to be on, it may be both, either shielding effectiveness or common mode chokes. Okay, and I'll give you homework on both of these, and we'll talk about it.